Okay. All right, I think that's good.
All right, do you want to start with questions? Or should I just go into the technique? I guess that means you want me to just go into the technique. All right. Okay, there's a little bit of vocabulary before we start. And remember, vocabulary is really important, so let's make sure we've got it. Do we know what a node is? What's a node?
Like any area between elements that's connected by wire.
Yeah, okay, so it's the 2 points on either, yeah, it's any area or point on either side of a circuit element. And it doesn't accumulate charge. So, okay, so let's say we have a circuit that looks like this. How many nodes does it have?
3.
3. You all agree with that? Good. Okay, so you should realize that just because I have a little corner here, that doesn't make it a separate node than this, because it's just a wire. So we can have a picture that looks like that, and it shows the 3 nodes, and I want you to show your nodes distinctly. Or we could have what's called a planar, or no, a linear graph, which kind of shows the relationships a little bit more clearly and kind of gets rid of all the corners. But the idea is that you can kind of shrink wires and stretch wires and put them into any shape you want without really changing the essential relationship between the elements. So, for instance, in fact, let me show it this way. This, electrically, is the exact same picture as this, even though physically it doesn't look exactly the same, right? R1 and R2 are in parallel. Now here they actually look like they're in parallel. Here they don't, but really it's not the physical relationship of them being in parallel that makes them parallel. What makes them parallel? What was the definition?
They're connected to the same 2 nodes.
Right. They're connected to the same 2 nodes, and so that's true in both pictures here. Okay, so what's a reference node? Okay, so that a node is just any one of the points between two elements. What's a reference node?
A node that you use to be 0, like your base
Yeah,
voltage.
it's just a node that you say, oh, that one's the reference. That you're going to say that everything else in the circuit is going to be measured in reference to that node. And so we call that 0 volts. It doesn't necessarily have to be 0 volts, but for the purposes of just identifying a reference, and for this circuit, all the other voltages will be measured relative to that reference node. So it's just some arbitrary node. It really, whoops, I forgot that one. It could be any of them. I could consider that the reference node, I could consider that the reference node, or this one. Usually, I don't know, intuitively we kind of like to make the reference node the one that's at the bottom. But it doesn't have to be. Any node can be the reference node. It's just a node that you pick to be the reference. And then, okay, now here's a really important concept. A node voltage. Okay, well, we understand what voltages are, right? We know that they have to be between 2 different points, because the definition of voltage is the amount of work it takes to move a charge from one point to another. Okay, so make sure you know the definition of voltage. And by the way, if I ask you for the definition of voltage and you say it's a potential difference, I don't like that, because it doesn't really explain. Like if I don't know what potential difference is, I won't know what you mean. So assume I don't know what potential difference is. Okay, so I'm showing the voltage across R1. Okay, and here's the voltage across R2, and here is the voltage across R3. Does it bother anybody that I put the plus here and the minus there? Or do you think it should be reversed, or does it matter? It doesn't matter, because I don't know what the voltage is. I do know that for a resistor that follows Ohm's law, the current has to be pointing into the positive terminal of the voltage, and so you might say, well, if you put the plus here, then that means you know what direction the current is, and you don't necessarily. And the answer is, well, I don't know what V3 is. V3 might be a negative value. So just, you can arbitrarily pick the polarity or even the direction on your current, and then when you solve for the value, you will see whether you chose the correct direction. And if you did, like if this is positive terminal, then V3 will be a positive number, but it might turn out to be negative. Okay, so so we know what voltage is. What's a node voltage? It's the voltage of the node. What? Janelle? Tell me.
Just the voltage of the combined, or of the elements between the nodes?
No. V1 is the voltage of the element between this node and this node. Anyway, the node voltage is the voltage of a node relative to the reference. In other words, one of the points is already chosen that you're taking the voltage between. And then the other one is just the node that you're identifying the node voltage of. So here's a node, let me call it VA. Let me call this node A, and so the node voltage of that node A I'm going to call VA. And then I guess maybe I'll call this VB. What is the voltage of VA in terms of these voltages that I'm showing on the circuit?
V2 and V1.
Yeah, it's actually, because we know since these are in parallel, it's the same voltage, so V1 and V2 are the same voltage, and it happens to be the voltage of VA. What about VB? Is VB equal to V3? No, because V3 is the voltage between this point and this point. The voltage of VB is the voltage between this point and the reference. So VB is actually V3 plus V2. Is this VB? Yeah, it is, because it's the voltage between that node and the reference. So that's all the definition of node voltage means. It's the voltage of that node relative to whatever you identify as the reference. And so it is important that you identify a reference node in your picture. Okay. Mesh. What's a mesh?
It's a loop with no loops inside.
Exactly. That's exactly right. It's a loop with no loops inside. And of course, we all know that a loop is some closed path. So here, how many loops do we have? 3. How many meshes do we have? 2. Right. Okay, so we now know what a node is and a node voltage. And we just agreed what a mesh is, and then what would be the dual of a node voltage? A mesh current. So what is a mesh current?
Clockwise current in the
Yeah, it's a current in a mesh. Okay, but what does that mean? Well, we usually show it by circular arrows like that, although, you know, because I have this square, I mean, I suppose I could do that, but nobody does that. Okay, so we've got a current that circulates in a mesh, and I'll call this IW, because I don't want to use A. And then here's a current here that circulates in this mesh, and I'll call it IK. So I've got 2 mesh currents, IW and IK. So what this is saying is that IW is circulating in this mesh, IK is circulating in this mesh. What's the current in this branch? And I'll just call this I2, I guess. No, IB for branch current.
IK minus IW.
Yeah, exactly. So IB is IK minus IW. Why minus? Well, because IW is going in the opposite direction as IB. So IB is a branch current, IK and IW are mesh currents, and in general, a branch current is going to be some combination of the two mesh currents on either side. Now, of course, we've got a branch here, and it doesn't really have a mesh on the other side. So the branch current here is just going to be IK. So sometimes the branch current is, if you've got some branches on the perimeter, in other words, they don't have another mesh on the other side, then the branch current and mesh current will be the same, but most of the time, branch currents will be the combination of two mesh currents. Okay. And then we need to understand what a super node is and a super mesh. And I'm going to stick so I'm making my picture a little bit bigger so that I can show you the definitions of these two important vocabulary words. Anybody know what a super node is?
What encloses a voltage source? Node.
It's a voltage source and the two nodes on either side. Do we have a voltage source here? Yeah. So a supernode, oh, in fact, I actually added another node here. It's this thing right here. That's a supernode. Because it's a voltage source with the two nodes on either side. And it really wouldn't matter whether this was independent or a dependent. It's still a voltage source, and that's all you need. So maybe this is KV4. Doesn't matter, it's still a supernode. It's any voltage source. In fact, maybe I'll emphasize that, not just a voltage source, any voltage source, whether it's a dependent or a independent source, and the two nodes on either side. So there's a supernode. And so if we go with that dual concept, what's a super mesh? Basically, it's the same words, but you're going to interchange current and voltage, so it's any current source and the two meshes on either side. So, do we have anything like that here? Yeah, we have a current source, and we've got two meshes on either side, so a super mesh, I'll do it in kind of a dotted black line. There's my super mesh. Okay, now that we have that vocabulary, I am going to give you the procedure for doing node voltage analysis or mesh current analysis. These are both procedures that are very systematic, straightforward, step-by-step procedures that if you follow them and you understand how to apply each step, you'll solve any circuit's problem. That is finding a voltage or a current anywhere you want, no matter how complicated the circuit is. So that's why you're so lucky that you're here today, because I'll explain it to you and you can ask questions, and you're going to leave today really knowing and understanding these methods. And it's going to get you through the rest of the course. All right? Okay. So node voltage analysis is the dual of mesh current analysis. Okay? And in both of them, you follow 5 steps, and here's how you remember them. Do like the Super Kaufman. don't tell anybody outside this class this mnemonic. Nobody else knows about it, except Keith. He uses it. Do like the super Keith when Keith Mueller teaches the class. So, okay, but what this stands for, these stands for the 5 steps. The D here stands for draw. The L stands for label. This D stands for dependent. This stands for super something. And this stands for Kirchhoff. Okay, so if you've got, I don't know, let me try this. I'm going to make a little chart here for the 2 duals. Okay, so for the step, okay, so these are both step-by-step procedures that enable you to solve any complicated problem. Circuits problem. Okay, so what I'll do is I'll just put up a problem and we'll do it. I'll do it and follow each of these steps and explain what I'm doing. Okay, so. This is the one I wanted actually. Sorry, this is the one I wanted. Sorry. Okay, I'm going to put a different thing, I'm going to do this problem a couple different times with different things in this spot. So for now, let me leave that blank. X. Okay, so we want to find, well, let's just find the y. And for the case where this is a dependent source, and it's a current source, and the arrow's pointing to the left, and it's 1.5 times IQ, where it depends on that current there. Okay, so this is the picture, this is the given information, and I'm asked to find Vy. All right, so this isn't really the most complicated problem in the world, but it might look a little bit harder than what you've seen so far. But you know something, no matter how complicated it looks, you don't have to panic. Because if you just follow these steps, do like the Super Kaufman, or draw label dependent Super Kirchhoff, which of course doesn't flow as well as do like the Super Kaufman. Why duh instead of the? Anyone know? You know who Willie Brown is? He's a very powerful political figure in California, and he used to be the mayor of San Francisco, and when he was a mayor, they called him the mayor. He's African American, is sort of like Detroit. Anyway, okay, never mind. So that's why duh, because we're in San Francisco, and if there's the mayor, we can have the Kaufman. Okay. Okay, so what is it that we have to draw? Well, you just draw the circuit, so that's done. You do that for both cases, just draw it. Make sure you've got everything labeled correctly. That's the first step, okay? So we're one down, 4 to go. Label. Okay, if you're doing node voltage analysis, what you want to label are all the node voltages. If you're doing mesh current analysis, you want to label all the mesh currents. So which one do you want to do first? Let's do node voltage. So I'm going to label the node voltages. Well, to label a node voltage, first I have to have a reference node, right? Because nothing's going to make sense unless I have a reference node. So let's just pick, or I'll pick that as my reference. Now I can go ahead and label all the node voltages. Let me first label all the nodes. Let's see, I've got one here. How many nodes do I have? It looks like I've only got 3. You agree? There's really only 3 nodes in this.
About between the voltage source
There's no
and
voltage
the-
source.
around the current source, the triangle one I'm forgetting.
Oh, the dependent
Yeah,
current source?
The dependent source
Well,
and that.
Here, you mean?
Yeah.
It's the same node as that.
What about between that and a resistor? Isn't that the,
This one?
yeah.
Like you're wanting with this one here?
I know that that would be kind of joined to the other one.
Yeah,
but
so it's the same node.
wouldn't you want that one kind of more there so it's in between the other two as well, not at the other one? Oh, never mind, because then you're between.
It's the same. I mean, I could actually redraw the picture so that it looks a little kind of more clear, sort of like that.
It's like one big node.
Yes.
Yeah.
It's the same node. Right, well, I didn't change anything, right? Right. I did not change anything. It looks a little bit different, but it's the same node, so whether I show it like that or like that, I mean, it's still, this is the same node as that.
It doesn't matter that it's not in between two elements.
It is in between, because remember, you can shrink wires,
Yeah.
and it's the same relationship. So if I, or change the shape of the wire, so if I kind of compress the wire and kind of make it more directly attached to that, and then this one more directly attached to that resistor, it's still, I haven't changed the essential electrical relationship between anything, but now it looks more clear, like, oh, that's just one node. But it was one node before as well. It just didn't look like it. It looked, okay? Sleep on it.
Okay.
Okay, I'm gonna change the picture back because I kind of want to emphasize that idea that, you know, if you show 3 dots in all 3 of those places, it makes you think that there's 3 nodes, but there isn't. There's just one. And I don't care where you put it, I'll put it here now, it doesn't matter. It's just one node. There's only 3 nodes in this. There's the reference, and then there's 2 others.
Each node is like at the same potential, right? So like everything connected by wire is at the same
Yes, yes.
potential. So it's
Right.
they're
So if I
expecting-
showed a dot here, it's still the same potential, so it's the same node.
Yeah.
Exactly. So I don't want to show more than one dot because then it'll make me think I got more than one node and I don't. I mean, you could show it if you want to, but I don't want to. Okay, so, okay, I haven't actually labeled my node voltages yet though. Let's say I'll label this node A and this node B. So the node voltage would be V sub A and the node voltage here would be V sub B. Okay, so now I've labeled my node voltages. I love checking off checklists. Dependent. Okay, this is what you have to do for any dependent source. You have to write the controlling quantity in terms of, in this case, node voltages, in this case, mesh currents. So write the controlling